As you introduced me, I'm Lucio Bustaffa, and I've been working in Blue Box, one of the company in the Swegon group, for 15 years, more or less. And what we do in Blue Box is, I can say, taking care about cooling on a 360 degrees closed loop, because we start from comfort cooling, we go through the industrial application, and in data cooling too. So what I want to present to you today is not what we do in Blue Box, because I'm not allowed to do it, but is to give you some hint. Some of my colleagues have done it before, and to give you some hint on how to manage data cooling. I don't know how many of you are data cooling managers here. Someone of you? But it is interesting on many different points of view, because technology is updating day by day, and sometimes what happens is that we are not completely updated with the technology in data centers. And when I started preparing this presentation, I was quite astonished by some data about the data centers. And I don't know if you have got an idea. I'm on the stage from more or less 60 seconds. Have you got an idea of how many emails have been sent during these 60 seconds all around the world? Someone of you? Someone can guess a number? Okay. Including spam, yes. More than 200 millions. Okay. So I think it's more or less as if every inhabitant of Sweden have sent more than 20 mails during these 60 seconds, but some of them is too younger to do it. Some of them, if you give them a tablet, probably will use to cut the vegetables, okay, inside. So no one has got an idea of what's happening in the web if you don't keep in touch with these kind of numbers. And it is increasing faster and faster. It is increasing with a very high speed. So we cannot forget these numbers, because we always keep in touch with it day by day. These are other numbers related to the same question. So every 60 seconds, 350 gigabytes of data are added only on Facebook. It's incredible, the number of photos that are pushed in the web every single second. Okay, so these data are awful and are just changing the way to manage the data center and to approach to data center technology. Because of course this means that we use energy, and powering the data center is one of the most difficult but fascinating issues, according to me, because we are consuming to power the data power in the data center 1.5 the energy that a big city like New York City consumes every year, and we are producing the same quantity of CO2 produced by 50% of the US cars. So you understand that these are huge numbers, okay? And saving 1% of energy in data center, it means a lot of energy if you consider this kind of numbers. But how is it used? For sure, someone of my colleagues went in this discussion before, but we can roughly say that the HVAC and cooling consumes about, let's say, 30 to 40% of the total energy introduced into a data center. 6 to 13 is for the battery and backup. Lighting is maximum up to 2%. And the rest of the data center, of the energy introduced, is just used for the main purpose of a data center, so for the server and storage. How is it used into the server? You have got a picture just for knowledge. So the server uses more or less 60% of the IT energy introduced into a data center. But we can say roughly that cooling consumes none less than 30% of the total energy introduced. And if you consider that the energy introduced into a data center is almost completely converted in heat power, it means that all this energy contributes to the increase the temperature into the data center. Because if you consider that only the chillers are completely outside of it, but all the rest, humidification if needed, the cracks, the IT equipment, the UPS and lighting is always inside the building. It means that all this energy is converted in heating power into the building. And of course, it has to be removed. I think that it is very important to consider the data cooling as an environment completely different from what we are used to do with the comfort cooling. If we consider comfort cooling, it means that we have to create a stable condition for human being, okay, with humidity, temperature. Instead, if we consider a data center, the only thing we have to do inside of it is to remove the heat generated inside. We don't have to take care about anything else. Data center is not an ambient for human beings, so the only trouble that we have to afford is the heat removal, only this. Forget about all the other stuff, because sometimes some mistakes are committed considering these two ambients as not so different as they are. And sometimes it happens something like this, that due to an ancient conception of the data center that many years ago were full of paper because of the printers and because of the ancient servers or computers, were kept at a very low temperature. It happens if you go often inside in different data centers that you go in an ambient very cold and you don't feel comfortable because of the temperature of the data center. It's a wrong thing, because you are losing energy, you are wasting energy in that, in many cases. Some of my colleagues before spoke about temperatures for 16 degrees, 20 degrees, and it is not so uncommon to find temperature like this one in, let's say, legacy ancient data centers. But the right temperatures are we have not to decide which are the right temperatures. It's not up to us, nor if we are data center managers, neither if we are data center designers. Everything is set by the right people, because the ASHRAE set the right temperatures into the data center. And if we want to build, if we want to manage a data center, the only thing we have to do is refer to the ASHRAE rulings. There's nothing else. It's always up to the ASHRAE. It sets the temperatures for the A1 to A4 classification for fixtures in the data centers. Okay, so it sets not only the temperature conditions, but the humidity conditions too inside. Of course, it set a recommended situation, so from 18 to 27 degrees, and an allowable situation. So now we are going deeply in the definition of what does it mean recommended and allowable. Let's have a look on the enthalpic diagram. What does it mean? It means that this is the recommended envelope. So between 18 degrees and 27 degrees, we are right. With the current technology for servers, these are absolutely recommended temperatures. So if we have temperatures between 18 and 27 with a humidity level that go from, let's say, 30% to maximum 60%, we are in a right position in which the server works in the proper way. But it is quite interesting to have a look on what happened during the last years from 2004 to 2011 for these levels. Because they have increased a lot. So if in 2004 it was 20 to 25, now it is 18 to 27. It seems not so much, but I assure you that we are speaking about 2 degrees on one side and 2 degrees on the other side. It's a huge let's say, range of temperatures allowed. And if we look at the recommended temperatures are higher. What does it mean, recommended temperatures? We have to consider it under 2 different points of view. Because increasing the temperature, it means that we are increasing the average failure factor. But increasing the temperature, it means that we are saving energy. So we have to find the best compromise between these 2 situations. But what does it mean that the failure factor increases? For example, if we look at the allowed temperature is 18 to 27. Okay, so it means from here, more or less, to here. The average failure factor is goes from 0.9, let's say, to 1.3. But what does it mean? That this is the right average failure factor? No, this is the failure factor that is calculated with 24 hours a day, 7 days per week, and 360 days per year working in these conditions. So if you define, for example, a cooling system that is able to make your system stable in 25 degrees, let's say, or 22 degrees, 22.5 degrees for the most of the year, but you don't want to take care about the temperature peak that you can have during 3 or 4 or 10 days in a year, it means that you are not working in a very bad conditions, because this factor will not increase so much if you don't work all the year long in this kind of condition. So you have to be very careful in evaluating these kind of numbers. And how can we try to reduce this energy? We saw that this is a huge amount of energy compared to the IT. And how can we reduce it? In the presentation that my colleagues have done before me, some of these methods have been already introduced. We will go a bit deeper inside of some of them. Mostly we can do it increasing temperatures inside the rooms, the data rooms, increasing the cooling equipment efficiency, of course, and reducing the cooling distribution inefficiency that are very often encountered in data centers. We have already spoke a lot about PUE. What I want to introduce is just only a definition of partial PUE. It is just related to the PUE connected only to one kind of energy in the building. So in this, sorry for this, but if you consider the energy introduced in the building for cooling, and you sum it to the IT equipment power, you obtain the partial PUE. So it's a factor that is different from the PUE. It is just the opposite of the EER, for who is quite in touch with the cooling. Okay, so it's nothing else than the opposite of the EER. But generally, the data center managers like very much speaking about PUE, and they don't want to speak about EER, but it's just the same thing if you speak about a partial. Okay, these are numbers related to what has been discussed before. So I think we can run inside the most important topic. So the cooling system into the data centers. I think in a rough way we can divide it in 2 main systems, the mechanical cooling and the free cooling. They have got an intersection. They are not completely detached. The mechanical cooling is intended as everything which uses a vapor compression cycle, sorry. And it can be air-based cooling, water-based, or liquid cooling, depending on which is the media which transports the cooling power into the building. Gert spoke a lot about liquid cooling before me. And we will concentrate, we will focus on this, on water and air-based cooling. For free cooling, it can be based on air, and we have got direct and indirect free cooling, or we can have the water-based free cooling for free cooling too. Another classification can be made considering the location of the rack units, the crack units, sorry, inside the building. And it is very important to consider it because it can affect the efficiency of the system. Because in a perimeter cooling system, that something like this, where the crack system are just on the perimeter of the room, we have a room-oriented system, which have got, as all the other pros and cons. And I think the most cons that we have to consider is the airflow. As we investigated before with Morgan, a system like this one, if it is not updated with a containment, contained cooling, can have a very high rate of recirculation, decreasing the efficiency of the system. To take care about the recirculation and to avoid it, exists the row-oriented cooling made by the row cooling, the in-row coolers that increases, of course, the efficiency in terms of airflow mixing. Maybe they are less flexible because you cannot provide, you have to put it inside of the racks. If you increase the dimension of the data center, you have to provide new machines for every new rack, for every 2 or 3 racks that you put inside the data center. And they take a little bit care about the recirculation because, of course, they divide in a natural way the hot side from the cold side. Okay. Going deeper, you find the containment cooling. We will go just deeper on this because it is very interesting. It is both for in-row and for perimeter cooling. As someone of you asked before, it is a technology that can be combined with both in-row and perimeter. And in this way, we avoid the false floor and the pressure losses connected with it. Another step to the efficiency in terms of recirculation is, of course, the in-rack cooling. The in-rack cooling provides the cooler just inside the rack. And this maximizes, of course, the problems coming with the recirculation because it avoids complete recirculation. There's no possibility. But, of course, it is very low. It has got a very low flexibility because I have to combine one by one. And in terms of redundancy, it is quite risky because if it fails, it means that the server will fail. Okay, I can keep this with a 2-coil system, but the fans are just inside. So you have to be very careful in the decision of what system you're using. And the last one, we have gone just deep inside of it. The liquid cooling solution maximizes, of course, the recirculation, let's say, limits, not minimizes, sorry, the recirculation limits, and it increases a lot the efficiency of the plant. But I think it is a technology dedicated just for a very short slice of the total amount of energy consumption in the data centers because it is dedicated to hypercomputers and let's say some special technology. If we go to the free cooling instead, we have to divide between direct and indirect, which is the main difference. The main difference is that if you use a direct free cooling system, you have to accept that fresh air is introduced in the data center. And this is, of course, a limitation. Because because the fresh air takes with himself the pollutant. You can filter, of course, but you can have a very efficient filter, but it costs in terms of pressure losses. And of course, you cannot avoid introducing humidity. You have not a strict control on the indoor conditions. And you can have a indirect free cooling, water-based, so you have a chiller equipped with a free cooling section, or you can use a dry cooler outside to maximize the performance in free cooling. And you have to use the rack, the crack inside, equipped with a free cooling system, of course. Or you can use an indirect free cooling air-based, so the exchange happens air to air. So you can divide by the media. So if in this system you use only air, in this one you use air to water and to air, and in this you use air to air exchange. So you can divide, you can classify it in terms of the media that you use to transport the cooling. Which is the best technology? It doesn't exist, the best technology, because it depends on many of these different factors. Are you a co-locator data center or an enterprise data center? Have you got a containment? Are you focused on the CAPEX or on the OPEX? The HRI prescription are going to change during the next years. Which is your IT load density? So only after having answered to all these, let's say, questions, you can decide probably which is the best solution. And probably you will not find one. Probably you will find more than one. But if we look to what's happening in the data center market, is this, more or less, okay? This is taken by the SRIA analysis. And you see that let's say in terms of growth potential, the containment, the air side economizer, water side economizer, and the adiabatic evaporative cooling, or acrobatic cooling, as our friend likes to name it, are increasing a lot, are just increasing a lot. Liquid cooling, too, is increasing quite a lot, but it's just dedicated to a particular technology, and so we want to focus on this side. For containment cooling, we can have both systems. We just encountered during the last presentation the difference between hot aisle and cold aisle containment. We can roughly say that this is a system that is able to maintain a stable condition for the temperature in front of the racks. So if you want to focus on the temperature in front of the racks, you have to use a cold side containment. Instead, if you are focused on the temperature of the return air to the system to maximize the efficiency of the cooling machine, of the chiller or of the direct expansion solution, you can use a hot aisle containment. This is the main difference. But both of them, hot aisle or cold air, maximizes the efficiency of the system. And it is the best solution for a retrofitting, because many times the data center is just realized in a way that it is quite easy to divide the cold aisle from the hot aisle. So this is combinable with perimeter cooling and with in-row cooling, speaking about the hot air containment. And the same is valid for the cold air containment. Which is the difference? With perimeter cooling, I have to use, let's say, a false floor. So I have the pressure losses connected with the false floor, of course, and with the duct to connect the air from the top of the system, from the top of the aisle to the bottom. If I use in-row cooling, of course, I have automatically, let's say, division between hot side and cold side. So only putting the in-row unit into the servers, I realize automatically the hot and cold air containment. So this is the main difference. And don't forget, this is focused on the temperature on the front of the server, and this is focused on the possibility to increase the efficiency of the cooling system. So if now we go deeply into the different system we saw on the previous slide, I try to make a classification in terms of all these factors, so efficiency, CAPEX, OPEX, sustainability for retrofitting, and all the others. And of course, the direct free cooling system, nobody have any doubt about the efficiency. It is for sure the most efficient. The only thing I have to know is about the only thing I have to do, is just pumping the air into the system. So the energy I'm spending is just related to the energy I need to pump the air into the system. because sometimes I can avoid to extract the extraction because I can put a, let's say, a pressure damper here and to move the air only with these fans. But if we consider the contamination, the retrofitting, the humidity introduction, the strict control of the air indoor air, it is of course not the best solution, this one. Where is it mostly used? It is used where the servers are changed quite often, are renewed quite often. As my colleague said before, in some situations the servers are changed because of the obsolescence of the servers, okay? So if we are in a situation like this one, if we change the server every couple of years, we don't take care about the failure factor of the servers related to the temperature or to the indoor air condition, because we are going to change the servers for other reasons. And this is what happens in enterprise data center like Facebook, Google. They are mostly operating with the system like this one. But if we have got to take care about the indoor conditions, and if we have to avoid the mixing air, we are forced to go for a indirect free cooling system, and it can be based on water with a chiller combined with a free cooling section, or let's say a dry cooler that can be equipped with an adiabatic system that increases the efficiency of the system. And of course, in this case, we have to accept a lower level of efficiency because we have to cool down the water, of course, but we avoid completely the mixing of the air. So we maintain completely closed the data center, okay, and we have not to take care about pollutant, about humidity. And in a system like this one, sorry, we have to have 100% backup cooling, mechanical backup cooling, because if during a couple of days during the year we cannot use external air because of burning outside, for example, of pollutant, we have to be able to cover the total demand for the data center with a mechanical cooling system. So we have to provide 100% backup cooling. In this situation, probably we don't need 100%, but we need a high rate of that of the total cooling needed to be covered by a mechanical cooling system because of the inefficiency linked to the water-free cooling system. And it is mostly used in high, let's say, in not in hyper, but in big data centers, where we need the separation between the indoor and the outdoor. The same separation we can obtain with a indirect air-free cooling system where water is not used. So here the exchange is between air and air. So we have got, let's say, a scavenger airflow that is used only to cool down the indoor air. So we have got a complete separation, and we are able to obtain maximize the free cooling benefit. In this way, we have all the advantages coming from the separation of the fluxes. So the indoor air is completely separated from the outdoor. And we take the advantages of a system with, let's say, a medium-high efficiency, of course, that can be increased with the adiabatic cooling. We made something like an exercise to compare, because, of course, to take a decision, you have to have some data. You have to consider some data to take the decision on which technology to go for. And we made a simulation on, let's say, a medium data center, 400 kW. We can say medium or medium-high, medium-large data center related to our to Europe, okay? Because of course, if we speak about United States, probably this is a small data center. But in our country, I think that 400 kW it can be considered in the boundary between a medium and a large data center, let's say. And it is equipped with 80 racks, disposed on 4 different rows with a containment. So it is a cold and hot containment data center that we simulated under particular conditions. The 2 systems that we considered are a very efficient, probably the most efficient free cooling system based on the water technology that you can find on the market in the current market, that uses crack inside to move the air and to release the energy into the building, and that uses chiller equipped with free cooling to produce the cold water outside of the building. So the system is made like this one. We have got free cooling chillers outdoor, and we have got 4 crack units inside. This is a perimeter cooling based on crack units with a hot air containment, and the cold air is delivered into the building through a false floor. We have got a redundancy. As my colleagues underlined before, you always have to consider the redundancy of a system in a data center. Here we consider it an n+1 redundancy. What does it mean? It means that if you make the sum of the total power delivered that the chiller can deliver, you obtain 1.5 the maximum cooling power requested by the data center. If you remember, you have got a 400 kW, and here we have got more than 600 kW available. Of course, we are making this free chiller running together, so the logic is not let's say the failure activation of a chiller. So they are always active. So to increase the efficiency of the system, because if every chiller runs in a partial mode, it has got obviously a highest efficiency. And the same is for the indoor units. The sum of these is higher than 400, but they can run in partial load mode. And we considered the pump to pump the water from 13 to 18 degrees inside and outside of the building, of course. And the comparison is made with a system like this one, using 4 different units, every one able to deliver 135 kW at the maximum cooling power. But they are running every one for 100 kW, so to supply the 400 requested kW by the data center. In this case, we are extracting air for 38 degrees and we are delivering air for 25 degrees. So we are totally compliant with the ASHRAE conditions because we are allowed to deliver air up to 27 degrees, but we take a margin. So we are delivering for 25 degrees with a delta T of 13 degrees. When you consider an air free cooling system, it is important always to look what the delta T, because on the delta T is based, of course, the airflow of the system and the energy consumption. We simulated the same data center in 4 different conditions, 4 different geographical and climatic areas. So in London, in Munich, in Frankfurt, sorry, in Stockholm, and in Moscow. These are we choose these areas because are probably the most important related to the IT cooling. If you know, as you probably know, London is one of the most important hub for the IT cooling, for the IT, sorry, and so the choice of the cities, of the areas, was made under this kind of considerations. So London, Frankfurt, Moscow, and Stockholm. And we consider different types of heat recovery, heat exchanger, let's say. So based on a single plate heat exchanger system for air-to-air exchange, a series-to-series plate heat exchanger. So both the air from the data center is crossing both of the exchanger, and both the external air is making just the same. or a system like this one with a series to parallel flow, because the external flow is not crossing both in series, but only the air from the data center. We made just this kind of analysis just to have a complete overview of what is happening with this kind of system. We performed our analysis with MATLAB, considering an adiabatic humidifier which is active for temperatures higher than 5 degrees. Why? Not because 5 degrees are not enough to have a total free cooling, but because the energy spent to have adding the adiabatic cooling is less than what we earn decreasing the speed of the fan. Okay, so we have a benefit in switching on the evaporative cooling system with the lowest temperature as possible. Of course, not lower than 5 degrees because of a problem with the ice. Okay, so these are the conditions for the calculation that we are going on now. And these are the results. We considered 4 different situations. This is the pressure losses for every one of the heat exchanger inside of the system. So every one of them loses 70 pascals in this situation, 80, 90, and 100. What does it mean? It means that if I've got 2 plate heat exchanger, I'm losing 200 pascals. And we made this comparison with a single, with a series, with a parallel, and with a chiller free cooling system, the first one that we considered before. And with a double, with 2 different filtering efficiency. So this is an F7 filter and this is an F6 filter on both sides, because we want to have a complete overview. These are the results in terms of energy spent by the systems. So this is the energy spent by the chiller free cooling. That's always the same, of course, because it is only for comparison. And this is the energy spent to run a system with a single plate heat exchanger. So this red one with F6 filters. These are for a series of 2 plate heat exchanger, and this is with a parallel of 2 plate heat exchanger. This is due to the cutting in pressure losses due to the parallel on the outside air linked to this system. Of course, it takes to a larger unit in terms of footprint. So it is not for free, this energy recovery, let's say. This is the situation in Frankfurt. This is the situation in London. This is the situation in Stockholm, and in Moscow and in Stockholm. In terms of free cooling map, okay, if you consider the geographical area where we performed our analysis, we are always in situations like this one. Probably this is not a free cooling map related to an indirect free cooling system. This is related to a direct free cooling. So if you have got a direct free cooling system in the geographical area we considered, you can assume to have 7,000 to 7,500 of free cooling hours per year. So mostly, more or less, let's say 80% of the total running time of the system, you can operate in direct free cooling. Of course, if you consider in indirect free cooling, just due to the losses in the exchange between air and air, you lose something in terms of available hour. And this is the reason why we equip the system with an adiabatic cooling system. So to increase the number of free cooling hours in a year. And the result that we obtained in terms of partial PUE, of course, not of total PUE, because we cannot take care about the other system. We cannot take care about battery. We cannot take care about the lighting or something like this. So don't trust who gives you a number of a cooling system and speaks in terms of PUE, of total PUE, because it's not possible to consider the total PUE. We should speak about EER of the system. But we can speak about the partial PUE just in the same way, because if you have got a system with an efficiency of a EER of 10, a free cooling system with a EER of 10, it means that you have got a partial PUE of 1.1. Nothing more than this. So, in a system like this one, going with if we consider the partial PUE with a traditional cooling, when I say traditional cooling, I mean the most efficient water-free cooling system that we can provide today. So, a traditional cooling is a little bit tricky, probably. But compared with the partial PUE of an indirect free cooling system, we have a decreasing of the partial PUE, of course. And if you think it is not so much, probably if you consider it in terms of energy saving for every one of this system, you are going probably to change your mind, because you are going to save more or less 40% of the energy spent for cooling, going from the probably most efficient system that realizes a very high partial PUE. Of course, this is a theoretical situation. And you are decreasing the total amount of energy spent in a system like this one by 38 or 40%. So I think it is a significant data. So that's all from on my side. Series to series plate heat exchangers. So both the air from the data center is crossing both of the exchanger, and both the external air is making just the same. Or a system like this one with a series to parallel flow, because the external flow is not crossing both in series, but only the air from the data center. We made just this kind of analysis just to have a complete overview of what is happening with this kind of system. We performed our analysis with MATLAB, considering an adiabatic humidifier which is active for temperatures higher than 5 degrees. Why? Not because 5 degrees are not enough to have a total free cooling, but because the energy spent to have adding the adiabatic cooling is less than what we earn decreasing the speed of the fan. Okay, so we have a benefit in switching on the evaporative cooling system with the lowest temperature as possible. Of course, not lower than 5 degrees because of a problem with the ice. Okay, so these are the conditions for the calculation that we are going on now. And these are the results. We considered 4 different situations. This is the pressure losses for every one of the heat exchanger inside of the system. So every one of them loses 70 pascals in this situation, 80, 90, and 100. What does it mean? It means that if I've got 2 plate heat exchanger, I'm losing 200 pascals. And we made this comparison with a single, with a series, with a parallel, and with a chiller free cooling system, the first one that we considered before. And with a double, with 2 different filtering efficiency. So this is an F7 filter and this is an F6 filter on both sides, because we want to have a complete overview. These are the results in terms of energy spent by the systems. So this is the energy spent by the chiller free cooling. That's always the same, of course, because it is only for comparison. And this is the energy spent to run a system with a single plate heat exchanger. So this red one with F6 filters. These are for a series of 2 plate heat exchanger, and this is with a parallel of 2 plate heat exchanger. This is due to the cutting in pressure losses due to the parallel on the outside air linked to this system. Of course, it takes to a larger unit in terms of footprint. So it is not for free, this energy recovery, let's say. This is the situation in Frankfurt, this is the situation in London, this is the situation in Stockholm, and in Moscow and in Stockholm. In terms of free cooling map, okay, if you consider the geographical area where we performed our analysis, we are always in situations like this one. Probably this is not a free cooling map related to an indirect free cooling system. This is related to a direct free cooling. So if you have got a direct free cooling system in the geographical area we considered, you can assume to have 7,000 to 7,500 of free cooling hours per year. So mostly, more or less, let's say 80% of the total running time of the system, you can operate in direct free cooling. Of course, if you consider in indirect free cooling, just due to the losses in the exchange between air and air, you lose something in terms of available hour. And this is the reason why we equip the system with an adiabatic cooling system. So to increase the number of free cooling hours in a year. And the result that we obtained in terms of partial PUE, of course, not of total PUE, because we cannot take care about the other system. We cannot take care about battery. We cannot take care about the lighting or something like this. So don't trust who gives you a number of a cooling system and speaks in terms of PUE, of total PUE, because it's not possible to consider the total PUE. We should speak about EER of the system, but we can speak about the partial PUE just in the same way, because if you have got a system with an efficiency of EER of 10, a free cooling system with EER of 10, it means that you have got a partial PUE of 1.1, nothing more than this. So, in a system like this one, going with if we consider the partial PUE with a traditional cooling, when I say traditional cooling, I mean the most efficient water-free cooling system that we can provide today. So traditional cooling is a little bit tricky probably, but compared with the partial PUE of an indirect free cooling system, we have a decreasing of the partial PUE, of course, and if you think it is not so much, probably if you consider it in terms of energy saving for every one of this system, you are going probably to change your mind, because you are going to save more or less 40% of the energy spent for cooling, going from the probably most efficient system that realizes a very high partial PUE. Of course, this is a theoretical situation. And you are decreasing the total amount of energy spent in a system like this one by 38 or 40%. So I think it is a significant data. So that's all from my side.